course is basically on the numerical modeling of multi-phase flows, and I think Professor Desjardins is quite popular in this area, and he has been working for quite a long time. And he kindly agreed to be here and teach this course and share his ideas. So we have kept the schedule like that. In the morning we will have 2 hours lecture, and then in afternoon you will have 1 hour lecture on the numerics, and before we proceed for the tutorial problem. So every day, almost every day, there will be tutorial problem, and for that we have to assemble in the computer center, which is just walkable distance from this place. So we'll see that how good it will be there in the computer center, because we do not know, because we want to teach 1 hour of numerics lecture. So if needed, and if we see that it is not helping there, of course there is a projector, but it may not give the classroom feeling that you have here. So in that case, we can see the numerics lecture here. Yeah, and then the tutorials will be there. So we have Linux machines there, so one of you will have an access to the machine, and then you can run the problem, and then probably during that time if you have any queries, you can interact with the queries. And so I will request our head of the department, Professor Ventina, to say a few words about this young course. And our mainly he will be telling about our department, and he will introduce our department to the participants who are basically coming outside from IIT Kanpur, and of course to Professor Ventina. So I invite Professor Ventina.
Okay, so let me first welcome you all to this GAN course, and those who are from outside the institute to the Mechanical Engineering Department and IIT Kanpur, and there are many familiar faces who are probably students here to this course. And also I would extend a warm welcome to Dr. Zadi to this campus. It's first time here in IIT Kanpur, so I'm sure he will take good care of you and all of you.
Yes, sir.
So,
Yesterday we had a good.
So I understand this is a course on numerical modeling of multi-phase flows, and I don't have to emphasize on the importance of this topic. I'm not a person working in the area of fluid mechanics and heat transfer, those areas, but still I can appreciate the importance of this. You can have this in turbines, boilers, or nuclear power plants and all. So you will get a lot of exposure to this area, I'm sure, and it's very important that most of the courses organized already have lectures, and I think Dr. Day has factored into the practical sessions where you will actually use software or commercial software.
No, it is basically based on the in-house code.
In-house codes, and that's very important because that is where you actually learn and experience whatever is being taught in the classroom. So it's a wonderful opportunity for you, and I am sure you will make good use of this here. Of course, we are one of the backbone departments of the institute. Mechanical engineering is a very classical discipline. I don't have to explain more about it. So briefly, we have about 39 faculty members in the department now, and we have 4 different areas of research called streams, just for the sake of convenience. One is fluid mechanics and thermal sciences, manufacturing sciences, solid mechanics and design, and robotics and automation. There are many state-of-the-art experimental laboratories in the area of IC engines, microfluidics, micro-manufacturing, impact mechanics, vibration. So I would also request you to find some time to explore the research area of different faculty members of the department on our webpage, and if there is time, interact with them and visit some of these laboratories, because this is also an opportunity for those who are working in industry and R&D organizations to establish a link so that you know what are the capabilities available in the department outside of this course. So that in future, if you want some collaborations or some projects, it will be very easy. So this is a very nice opportunity for you to explore the department. We have about 400 undergraduate students, 100 students every year we admit. About 60 master students we admit every year, and currently we have about 180 PhD students. So lot of intense research going on in various different areas of mechanical engineering and also interdisciplinary areas. Okay? So I don't want to bore you with all those details. We have a very good web page. Please visit the web page and then find time for interacting with the other faculty colleagues also. Right? IIT Kanpur is a very nice campus. Please explore. We have an airstrip with a couple of aircrafts. The only educational institute in India having an airstrip and some aircraft. So have a good stay here and also get a lot of exposure to the topic what is covered in this. Thank Dr. Day for organizing a series of CAN courses. This is your third or second one. So he's very active, and once again would like to thank Professor Sarins who have traveled all the way from Cornell here to participate in this. Okay, have a good time and thank you.
So now I will briefly introduce Professor Desjardins, but I think you are all familiar since you are working in this area. So Professor Desjardins is currently Associate Professor at Cornell University. Earlier he was at University of Colorado at Boulder, and he did his PhD, both Masters and PhD, from Stanford University. And then he was a postdoctoral scholar at the prestigious Center for Turbulence Research at the Stanford University. So he is a recipient of several awards such as the Junior Award of the International Conference on Particle Flows and National Science Foundation Career Award in 2014, Distinguished Paper Awards, Oscar Visualization Award. So he's at present serving as the associate editor and the member of the journal that is Atomization and Space from Legal House. And he's also the board member for the Institute for Liquid Atomization and Space Systems, that is called ILASH. It is quite famous, and those who are working in multiple areas are familiar with this. So with this brief introduction, I will welcome Professor Desjardins once again, and I'll ask him to share few thoughts with you before we break for the tea.
All right, thank you very much. Yeah, sure. So thank you for the invitation. Thank you for your kind words. And thank you all for attending. This is really, so that's my first time in India and in Kanpur. So it's a lot of firsts for me. It's pretty exciting. I've liked it a lot so far. I've been around the country, well, not the country, but I arrived 10 days ago, so I'm not jet lagged. I don't have any excuse. But I just arrived yesterday night in Kanpur, which was apparently very good timing because I got to enjoy a very nice concert. So. All right, so a few thoughts. Well, I think you all probably, I imagine, working in some area related to multiphase flows. I actually didn't start my academic career working on multiphase flows. I started working on combustion. And I was tasked, when I started my PhD at Stanford, I was tasked by my advisor, Heinz Pitch, to perform a logical simulation of this problem. This problem was, well, is still a n-heptane fueled flame. This is supposed to represent a very simplified canister type combustor. That's a very simplified model of the type of combustion system you would expect in a gas turbine engine for aircrafts. So this was based on an experiment that was funded by NASA back in 2001 or 2, something like this. This was going on in Chris Edwards' lab next door at Stanford. And so this is beautiful. I got really excited. I was more into the numeric side of things. I'm not allowed in labs because I tend to destroy things. So I was tasked to basically use the in-house code there to do larger dissimulation of this problem using, for those of you who have some exposure to combustion modeling, using flamelet type models, what's called FPVA, flameless progress variable approach. And so the code we had was already capable of doing some of that. What you see here, for example, the yellowish side of things is soot. We didn't really know how to do soot. It's gotten a lot better now. But the gas phase combustion process, we did reasonably well. The turbulent combustion side of things, we did reasonably well. Maybe I should explain first. So this is the stream of N-heptane that is swirled coming out of a liquid nozzle injector, fuel injector. And what you see here is a conical flame that's anchored because of swirl stabilization. So there's a co-flow of gas that is swirling and that is creating a stable position for the flame to sit. So that's how you can anchor a flame and avoid for it to blow off in your engine. So my task was to add a Lagrangian particle tracking model to keep track of the liquid droplets, evaporate them, and have them interface then with the gas phase combustion solver and run all this and basically get good results and publish it and finish my PhD. And what I realized is that by tuning the droplets, I could get any answer I wanted. So I did not, what I knew was the flow rate coming out of this nozzle, but the next thing I knew was some information down here regarding the droplet size distribution, the mass flow rate distribution, and the mass flux distribution of drops, and the velocity. Well, there's many ways you can generate a collection of droplets that match those different properties, and by choosing different spray characteristics in my Lagrangian representation, I could get pretty much any combustion process I wanted downstream in my model. So basically, that got me less and less interested in the combustion problem and more interested in the atomization problem, the problem of how do you actually form a spray and how do you predictively model this. So I started doing more and more work both on the area of particle-laden flows, so tracking large collections of interacting particles and droplets in turbulence, as well as problems involving direct breakup of interfacial flows. So how do we get from a straight liquid jet to something that looks like a spray? And so my approach has been pretty far removed ultimately from this problem because it is complicated. I've gotten more and more interested in the very detailed numerics that would allow you to compute all this from first principles. I think that we have so much computational resources becoming available nowadays that we're getting to the point where a few years from now we will be able to compute all that from first principles, from Navier-Stokes and pretty much nothing more. And to do that, we need to have the codes, we need to have the students with the knowledge of the methods, and so that's what got me more and more interested. And so that's what I'm going to talk to you about in the next couple of weeks. We're going to talk about methods for tracking particles, both Eulerian and Lagrangian methods for tracking particles, dealing with collisions, dealing with fluidization. So we'll look at methods that scale up to problems like this, where we have large numbers of particles interacting, colliding, bouncing off each other, et cetera, et cetera. But then we'll also look, so that will be this week. Next week, we'll look at how do we track a surface, how do we break a surface, how do we deal with surfaces interacting with turbulence, what are appropriate numerical representations of surfaces, scalable ways that you can implement a surface tracking code that can run on supercomputers. So we'll talk about pretty detailed numerics. I'm really excited about, Professor Day was pretty adamant about the need for a tutorial, a hands-on part in this course. And I didn't have that ready initially, and I thought, well, this makes in fact a lot of sense. So I got more and more interested in doing something like that. And now I'm really excited about the afternoons. So what I've done is I've put together a small or smallish code. Fortran, hopefully most of you have reasonable familiarity with Fortran. And that's a code that I think you can all pretty easily read from the beginning to the end. And we're going to add the methods directly onto that code. So I don't have tutorial problems. I don't have really questions to ask you. What I want us to do together in the afternoon is just actually sit down and put the code together. So I'll have day to day, so from day 1 to day 10, I have a code that I've given Professor Day. It's there. So that's, in a sense, the answer of the previous day's tutorial, if you will. But my goal will be to just guide you through the process of implementing a level set method, the VOF method, the particle tracking code, collisions, all those things. We'll actually do it. I've realized that I've never done that with anyone. I've never seen a course that did that. And so upon being prompted by Professor Day, I thought, well, that actually is exciting, and I don't think there's anything like that out there. So I'm pretty excited by that. I hope you'll apologize the fact that the course is a little bit, if you look at the corresponding course pack, you'll see that it's kind of all over the place. I don't have, in the past number of years now that I've been working in this area, I've never taught a numerical course on multiphase flows. I've taught a theoretical course on multiphase flows, and I've taught numerics for single phase flows, but I've never really taught this course at this interface between those two areas. And I think, again, this is a good opportunity. But I had to choose between putting more detailed notes together or putting a tutorial together, and I thought the tutorial made more sense. So you have the codes, and I think they're all downloadable from Professor Day's website or from the course website. So we'll be going through that. So what you'll leave with 2 weeks from now is all these actual working tools. What you won't leave with is a set of notes that discuss the very details of that. What you'll have instead is the actual papers that are the basis of all this. Okay. So hopefully we'll figure out how to make this work. I've kept some flexible time towards the end of each week so that we can have more interactive sessions and steer things in one direction or another based on your input. So we're looking forward to it. Thank you.
The idea is that we have participants from most of the top IITs, old IITs. For example, we have participants from KTP. One or two participants from KTP. Can you identify those? And so that, IIT Kharagpur, then IIT Bombay, then IIT Delhi, and IIT Madras. So we have participants from IIT Mandi also. There are 3 participants. And we have participants from NIT, the National Institute of Technology, from NIT Allahabad, right? Yeah. And then also from NIT Mizoram. And we have 3 participants from Aligarh Muslim University. Yeah. So apart from that, I'm not sure. I think you can identify yourself and then tell something. What is your interest, research interest, so that we get a feeling about it.
Oh yeah, that was going to be my plan anyway at some point to go around the room and.
You can just tell a few sentences and introduce yourself.
My name is Hitesh Kumar, and I'm currently a senior project officer at IIT Madras, working on flame acoustic multiphase interaction for combustion instability with Professor S.R. Chakravarti at the National Center for Combustion Research. And I did a PhD in which I have developed a numerical algorithm for interface capturing using a moment of fluid method for large density ratio. And in fact, I have followed many of your papers and Professor teach. Thank you.
My name is Pradeep. I'm here in IIT Bombay. I'm working on particular inductor force. We're working on the open source code from source code. And we're implementing the use the particle drag and weight model. I'm interested in those areas to learn and I'm working with Professor Partha Goswami. So I'm third year student.
Hi everyone, my name is Anandan. I'm a first year PhD student in Indian Institute of Science, Bangalore. I did my master's also in Indian Institute of Science only. I'm working in Gaurav Thomas lab, a multi-phase flow simulation lab. We have an in-house code based on CLS WOF, and we have an open source code Zeris in which we do atomization simulation. I am working specifically in multi-scale simulations of multi-phase flows.
Hello everyone, I am Kumar Tiwari. I am from IIT Delhi and I am pursuing my PhD under Sanjeev Tensor. And my PhD topic is modeling and performance analysis of cooling tower system. So rightly it is a NTPC project.
Hello everyone, I am Ramna Gawal. I am a student in IIT Mandi. So my work is basically modeling, LAS modeling in fluidity code and then simulating a bubble column reactor over. I am working under Dr. Gaurav Bhutan.
Hello everyone, I am Amit Kumar from IIT Mandi. I am working under Dheeraj Patil sir. My topic is multi-phase flow by a lattice Boltzmann method. We are developing a code, multiple relaxation type lattice Boltzmann method. My research topic is in pool boiling. Thank you.
I am Sandeep Gupta. I am research scholar in IIT Jodhpur, and I am working on microstages to the fluid simulation in poor simulation.
Good morning everyone, I am Pawan. I am from IIT Kanpur and I am working with Dr. Maladas on the field of modeling of blood flow.
Everyone, I am Mahendra Singh, PhD student in IIT Kanpur. I am working on drawing of food materials in rotary kiln and I am in the 4th year of my PhD.
Hello everyone, my name is Govind Sharma. I am working on particle modeling now. After that I will be working on with CFD coupling also, and I am working under Dr. Dheeraj Patil in IIT Mandi.
Hi everyone, I am Divyendu Ghosh from IIT Kharagpur. I am working under Professor P.K. Das and my interest is fluidohydrodynamics. So I am writing my own code and where the fluid interacts with some other fluids and capture those interfacial instabilities and more details of the flow fluid.
Hi everyone, I am Kush Kumar Devangan. I am working under Professor P.K. Das and I am working on compressible flow with the phase change. Diffuse is based on diffuse interface. That's where we are tracking the interface with the phase change with my own.
Hello everyone, my name is Sanjay Gupta and I am working with Dr. R.P. Chabra and in IIT Kanpur, and I am in 4th year and my working area is non-linear fluid mechanics. So like Bingham plastic fluid and power law fluid, and I am working also in single phase flow. So I want to explore myself in multiple flows. Thank you.
I am Mahesh Prasad. I am from IIT Kanpur only, from chemical engineering department. I am currently working on granular flows, so basically exploring the rheology and segregation part of granular particles in a shoot flow. Basically, I am working in a C language, where I am using discrete element method only, but I want to connect it somehow to the linear mechanics, so that's why I am interested in this.
Right now we are studying the mixture formation in low temperature commercial engines. For that we are studying flash boiling and the diesel sprays for that particular application.
Good morning everyone, I am Sumit Visishta and I am working as a research associate in the Department of Physics here, and I am working on large eddy simulation of using denormalized parameters of turbulent convection and isotropic and homogeneous turbulence. And I completed my bachelor's in mechanical engineering, and in my bachelor's I have developed a compressible flow solver using particle velocity method and an interface tracking code using level sync method. And I have also worked in the field of active flow control, and I developed one active flow control technique which enhanced the lift to drag ratios in air vehicles by nearly 60% at low Reynolds numbers, and I presented it recently at the aviation.
Mishra, a PhD scholar from NIT Mizoram. I'm working in the area of drawing of moisture objects under physics.
Good morning, everyone. My name is Swati Singh, and I am working on the topic droplet impact on liquid and solid surface. And I am working with Dr. Aruna.
Good morning, everyone. Myself, Priyanka Atmacharya. I am from IIT Kanpur. I am working under Dr. Maledas, and I am working in bubble dynamics using open code. That's the open source code.
Hello everyone, I am Akshay Tiwari. I'm a student from IIT Allahabad. Currently, I am doing two types of problem. One is the Lagrangian tracking of particles, nanoparticles in microscope. Another is to understand the droplet interaction with the surrounding fluid using level set method and phase method. So we are interested in doing the lecture for that purpose to understand the interaction between the two kinds of problems.
Although I've been working in the planning area, I am interested in turbulence and turbulence and also the model of turbulence. So I am supposed to explore the
Good morning everyone, my name is Sandeep Gupta and I am pursuing my MTech from Vaikush College and I am working on particle tracking and deposition in human lung area.
I am Bhaskar and I am working with Professor Dev as a senior project engineer, and I did the PhD on coal gasification, and very recently I am working on fluid bed gasification. So in this one I am particularly interested in particle dynamics.
Good morning everyone. I am Gopinath Sahu.
join us for tea.
All right. So we'll start. Okay, good. So first question I should have asked earlier is, can everyone hear me properly? Yes? Okay. The second question, which seems maybe more doubtful or more concerning, is, can everyone see what I'm projecting here? Can everyone read what I'm projecting? Or I guess the other way of asking this is, if you can't read what I'm projecting here, could you let me know, please? Okay, that seems fine. My intention is to write on this directly instead of using the whiteboard or blackboard. Well, I guess whiteboard here. My plan was to directly write on the PDF document, and then you can take the same notes if you want. You don't have to if you don't want to, and we can make them available. Whatever annotated documents comes out of our 2 hours of lecture, we can upload that and make it available to you directly. Okay. So I was very pleased to see during the first round of introduction that there's a broad interest in multiphase flows. I've seen, or at least I've heard, people express interest in interface-related problems. I've heard people express interest in particle-laden flows. I think there's a lot of very exciting research at the interface between those two areas. I think those are two areas of multiphase flows where the interaction between this notion of tracking the motion of either surfaces or points with interacting with turbulence, those questions I think are very much critical and important. And that's been where I've been doing a lot of my research in the past, at this point, 10 or something years, 12 years, 13 years. And so I'm glad to see that there's this mix in this room, this mix of interest. Okay, so let me tell you a bit about the structure of the course. So first of all, you should have a schedule like this. This is more indicative than anything else. It's not, don't take it as an extremely precise description of what we're going to do. I'll try to stick to it, but I've started from an outline that was pretty different from that, but then the idea again of trying to put the tutorial front and center in this forced some reorganization, and so things as a result are a little bit, basically I'm trying to give you some theoretical considerations and some numerics as a background, required background to the discussion related to the tutorial. So this is the idea. So the plan here will be 2 hours in the morning. Then this is where things are not yet fully worked out, and so we'll figure this out this afternoon. The idea is to have an afternoon lecture on numerics, so a specific discussion on how we're going to put the method together in a computer, and then actually doing it during the tutorial. I think there might be a lot of benefits from merging those two into a single unified session. Whether we can do that or not, we'll see. I've mentioned here that the tutorial, I'm saying up to 2 hours. I'm not quite sure how long things will take. Like I said, I've put together some code that I think is close to the simplest set of algorithms that can be used to describe multiphase flows. And as a result, they're pretty quick to go through, but pretty quick is still a relative concept. We're talking about a few hundred lines of code that need to be done every day in order to keep up with this plan. One thing I've tried to do is make sure that, so we're going to cover it in the first week. I should have mentioned that. I think maybe I have already. The first week is going to focus on particle-laden flows. Okay, so we're going to look at particles, solid particles interacting with one another So I've heard people express interest in discrete element problems. I've heard people express interest in particles in turbulence and DNS with point particles and things like that. So that's what we're going to talk about. We're going to talk about that from the perspective of Lagrangian particle tracking. Then we're going to talk about that from the perspective of Eulerian particle tracking. I heard someone mention something about two-fluid model, so we're going to put probably the simplest version of a two-fluid model together. And we're going to test it. I'll try to convince you that it's not necessarily very good, but you can obviously do a lot of other things with Eulerian methods. We'll talk about collisions. I have something planned for the last day. I've mentioned this as I didn't want to be too, I didn't want to commit too strongly because I feel that there might be interactions during the week that might steer us in different directions. But I have a couple of things that I'd be interested in showing you with the code that you'll have developed by the end of those 4 days. At the end of both weeks, instead of a discussion on numerics, what I have is this "what is missing" title, which is basically going back to everything we've done and thinking about where are we now compared to what one might consider as state of the art. So that's what I'm going to try to show you. So this will be basically me going through seminar slides from recent talks, telling you, okay, those are some of the latest developments that we've gone through with those techniques. Okay. Second week, liquid gas flows. We'll look at interfaces. We'll deal with interface tracking. So this will be, the theme will be level sets, volume of fluid. I've heard people talk about level set, talk about CLS-VAF. I've heard people mention JERIS. So this is all relevant to those questions. So first day will be the concept of a level set. The second day we'll talk about reinitialization, which if you don't know about it, well, you'll just wait 6 days. We'll talk about volume of fluid. This will be the only place where I don't go down to the very, very details. I will sacrifice a little bit of details here, and I'll give you a prepackaged routine, essentially, that will do a lot of computational geometry. It wouldn't be very complicated to have you write everything from scratch, but it would probably have taken another day or two. So this is the one place where we'll take this shortcut. I'll tell you, here's a routine. If you give that to that routine, you'll get back this. Okay? But everything else, again, you'll be writing. The issue is that it's easy to implement a volume of fluid method that is pretty bad. But I don't want to leave you with this impression that volume of fluid is bad. It is not. But the fact is that it's a complicated scheme to put together. So we'll talk about that. Then we'll implement a ghost read method. We'll put together a methodology to deal with surface tension in a way that's reasonably accurate. We'll calculate curvature, and that will give us access to oscillating drops. And then again, what is missing, and then we'll play a bit with, on the last day, we'll do some atomization problems. All right, so that's the plan. Before we start, I want to welcome interruptions and questions. And first, now, is there any concerns with this outline? Any questions? Anything that stands out as missing, or anything that stands out as out of whack in any way? Evaporation. So I have notes regarding evaporation in this enormous collection of stuff. And that would be tomorrow morning. The issue is we have 2 hours tomorrow morning, in which I want to talk about also drag, compressibility, turbulence. So if there's enough interest in the discussion regarding the typical Serignano type vision of evaporation for a single droplet, we can get to it. I have the material ready, so this is something we can do, yes. So maybe I can move that up in priority a bit if there's enough interest. We're not going to implement evaporation, but we're going to talk about the related equations. At least it's in the notes.
I think then if there is enough interest, then
Okay. So that's 2. 3, all right. 4, 5, okay. So we'll just have to go. I think we can make it work. Okay. Let me see what else I wanted to say on this. I think that's essentially it. So one thing I want to mention. This, and I mentioned that before. This is not a course that I've taught before, and as a result, it's a collection of notes that come from different places. The first set of things that I planned for today, which is very much just high-level introductory material, is, in fact, I didn't even bother changing the headers and the footers of the documents. So this is just chapters, course notes taken from various courses that I've taught at mostly Cornell in the past few years. So this is something I last taught in the fall 2015 on the fundamentals of multiphase flow dynamics. This course didn't have any numerics or didn't have much numerics in it. Okay, so this afternoon, for example, we'll talk about the underlying code that we'll be using as a starting point for our tutorials. This code was given as a homework project to the students taking a CFD course with me, same thing at Cornell. So the corresponding notes that I have for this afternoon is just the homework, the text for the homework that was given to the students. Okay, so there'll be a collection of different documents like that might seem a bit unexpected maybe, but hopefully there's enough supporting material. For the most part, the documents that I've provided for the afternoon and the tutorial, they're going to be papers essentially. I think for the most part, we're talking about topics that have made it into textbooks, but I would challenge you to find a good textbook that covers both particle-laden flows and interfacial flows in a way that's comprehensive. This is something that I think at this point has yet to be written. All right. Okay, so I think we know what multiphase flows are, so this is one of the places where I'm not going to spend any time really. Any situation where we have more than one phase involved in a flowing system is where we're going to talk about multiphase flows. I have some discussion here of whether solid phase and liquid phase and gas phase is. I'm going to assume you know the distinction just has to do with the enthalpy of the system, and it has to do with the strength of the intermolecular forces. When we talk about multiphase flows, it's implied that we care about phases that can flow. And so in that regard, solids seem maybe a bit unexpected, but I guess it's clear that we'll talk about flowing solids from the perspective of dispersed solids. So we'll have particles, we'll have little chunks of solids that are moving around and behaving as a fluid as a result. Okay? One thing that I should mention is that as you go from solid to liquid to gas, the compressibility goes up. And so that means that it's very unlikely that if you're looking at, say, underwater slurry transport, underwater sediment transport, if you're looking at any situation where you have solid suspension in liquid, it's very unlikely that you'll care about compressibility. If you're looking at a situation where you have either solid or liquid dispersed into a gas, you'll have to start asking yourself whether compressibility might play a role, because now the gas phase can be compressible. So you'll have to ask yourself questions regarding the Mach number. The assumption I've made, which is a significant simplifying assumption, is that we'll work under the assumption of an incompressible gas phase. So that takes away a lot of the complexity. It also might remove some of your interest in what I'm going to talk about. I have some plans on the very last day to talk about what happens if you have a compressible gas interacting with a liquid. So we'll do a little bit of that. But we won't go into an enormous amount of details. There's a lot of you interested in combustion. So another interesting phase of matter that you might be interested in looking at in the future is also plasma. We're not going to be talking about plasma. Okay, so we've described 3 phases of matter. Now what's going to happen is as soon as you put 2 of them together, you're going to start seeing some multi-phase flow. So here I have a few examples of liquid gas flows, solid gas flows, solid liquid flows. We'll talk about a range of these. But essentially, if you have a solid dispersed in the liquid, we'll essentially think of that as a particle-laden flow. In the same way, if you have a solid dispersed in a gas, we'll think of that as a particle-laden flow. They will be significantly different. The main difference being that the density ratio between the solid phase and the liquid phase is going to be much less than the density ratio between the solid phase and the gas phase, and that's going to have a significant impact. And situations wherein we have a gas and a liquid together, we're going to look at that in 2 different ways. Either the liquid is going to be in the form of a collection of tiny droplets that are stable. We'll talk about them having a small Weber number, meaning surface tension will dominate, and those droplets will be stable to perturbations. In situations like that, we'll essentially be looking again at the particle-laden flow with a high density ratio. We can have the opposite situation where we have tiny bubbles of gas dispersed in the liquid. Again, if they're small enough, they're going to have a low Weber number. They will be stable. They will be treatable as a collection of spheres. And as a result, we'll again be thinking about a particle-laden flow. And in situations where we cannot assume that one phase is a dispersed collection of essentially tiny spheres, we'll have to start thinking about what the interface looks like. And this is where we're going to have to say, well, this is now no longer a dispersed 2-phase flow. This is going to be a flow where we're going to have to deal with the interface. Okay, so this is, we're going to spend a lot of time essentially in this category because it does allow us to talk about both particle-laden flows and interfacial flows. One quick note, if you get here a situation where the 3 phases interact, and I think I heard someone mention something about droplets impacting on the solid surface. This is the type of thing where you're going to have to deal with the existence of 3 phases simultaneously. And that's a big deal. It turns out that this is a very non-trivial extra complication. So my plan was not to discuss much about a triple phase flow. But if you have 3 phases together, there's probably going to be a point where those 3 phases meet. And if those 3 phases meet, they're going to have to deal with the dynamics of the point where the 3 phases meet. So you're going to have to start dealing with contact line physics. And so that gets us into the topic of wetting, meniscus, and things like that. So I just wanted to give a little example. You all know what a meniscus is. If I have a wall, so let's say solid substrate, and allow me to put an interface here. There we go. We're going to put gas on top, and we're going to put liquid below. If I look at something like this, the issue is going to be what happens right here at that point. And what happens will depend on the very detailed physics at the molecular scale of the interaction between the gas and the solid. There's going to be a tension force between those two at this interface. There's going to be a tension force between the gas and the liquid, what we're going to commonly call surface tension. And there's going to be a tension force between the liquid and the solid. The combination of those three effects will lead to a very specific phenomenon, which is that the interface will take on a certain angle, which will refer to a contact angle. So really, we will not see something like this. Instead, we will see probably an interface shape like this, where we will have an effective contact angle that I'm writing here as theta. I don't know if you can see this. Let me zoom in a bit. So this issue of contact angle is important. It is problematic in a number of ways. One of the main ways in which it is problematic is that the specific physics related to contact angles and their dynamics is the fact that they're not inherently contained in Navier-Stokes. Those are molecular scale processes that we have to reintroduce in Navier-Stokes. We cannot start from Navier-Stokes and say, well, let's nail this problem with resolution and we'll get the right physics. This is not going to be the case. One interesting consequence of this is that if I add gravity to this problem, so if I have gravity pointing down, and now if I force my wall to slide up at a velocity u, you're going to see right away in what sense Navier-Stokes becomes problematic. The viscous effects in this flow require a no-slip boundary condition. Okay, so because of viscosity, we would naturally expect a no-slip boundary condition. That would force the liquid to move up. But the molecular scale physics will tell us that this is not true and that we need to have a certain contact line angle that develops in this flow. And it will work against the departure from that angle. So it will work against the deformation of the interface. So this you'll capture in a capillary number. So this capillary number will tell you how much you need to worry about this contact line problem. Mu here is my viscosity. So that's my dynamic viscosity, and sigma here is my surface tension coefficient. But what you can see is that if I move this interface, or if I move this wall, and I'm not able to entrain the liquid forever, so if at some point the interface just sits down at its contact angle, that means that locally I'm violating the no-slip boundary condition. Okay. So at that point here, locally, there is effective slip. So our classical equations, we'll have to rethink them in some way. I don't want to talk much more about this. We have worked recently on how one can model this process. There's a lot of people who've done an extensive amount of research in this area. So I'm happy to take questions on this or discuss this one-on-one in the next few days. But for the most part, we'll try to stay away from 3 interacting phases simultaneously, in particular for this reason, because it does require at some point for you to re-inject the physics that Navier-Stokes doesn't contain. Okay. A problem that occurs naturally if you're looking at the multiphase flow is the fact that the phases tend to change from one state of matter to another. So that's something that is inherent to the study of multiphase flows. I can probably, a very compelling example of that is if I take a biomass particle, nice and solid. The entire idea of designing a gasifier or any type of biomass reactor will be to extract in vapor phase the to extract the vapor phase from this biomass. This can happen directly through devolatilization. aka sublimation of the solid phase, or this can happen through liquefaction followed by evaporation of the liquefied biomass. If you're looking at a spray combustor, the entire point is that you're going to have a liquid. This is a fuel spray. You're going to want to turn it into a vapor in order to combust it. So a lot of what we end up doing with multiphase flows has to do with taking one phase of matter and making it available to a process in some other form. So continuing quickly with this, really what I've mentioned is we're going to have to think about two strategies, and this is how I've organized the 2 weeks. The first strategy that we're going to deal with will assume that we know enough about the topology of the interface that separates the two phases. In this situation, we'll typically say that it is safe for us to assume that the phase interface is just a collection of a large number of spheres. That's essentially what we're going to say. And then in this situation, we're going to be looking at particle-laden flows. So we're going to be looking at flows laden with solid or liquid particles. It could also be a liquid flow laden with gaseous bubbles. That works the same way. And so typically what we're going to do here is we're going to assume those particles to be spherical. This can be lifted. You don't have to say that they're spherical, but the idea is you're going to have to say that in some way the shape of the particle is known as a priori, and then you're going to be dealing with the tracking of those particles of known shape. So that's going to be the main way in which we're going to be looking at particle-laden flows. The second approach that we're going to talk about next week will involve acknowledging that we don't know the topology of the phase interface at all. We know nothing about it. If we don't know anything about the topology of the phase interface, we're going to have to solve for it as part of our model. And so we're going to have to introduce an equation of which the goal is going to be to tell us where we have one phase, where we have the other, and what is the shape of the interface that separates the two phases. So this we'll typically see in situations where we have a liquid gas flow. And so this, for example, is highly relevant right here. If I zoom in a bit, if you're looking here at the atomization process of an N-heptane spray, well, right here we have some very complex distribution of liquid that takes a non-trivial shape that we don't know a priori. And in fact, we struggle to know a priori what the drop size should be. So this entire problem here, we cannot hope to tackle it by simply assuming what the drop size is. Or let's say if you do that, you're basically assuming the answer or part of the answer as part of your model, which is fine provided you have an experiment, but it certainly doesn't make for a predictive tool. And so that's pretty much where I started becoming more and more interested in the topic of atomization. So here we're going to have to solve for where the phase interface is. Same way here, we're going to have to solve for where the phase interface is. We cannot know a priori much about what shape it should take. However, if you're further downstream, it is reasonable now to say that your interface takes the form of a collection of spherical droplets. And so provided that either another model or an experiment has told you something about where the drops are, what shape they have, then basically it becomes a tracking problem of a lot of particles, a lot of liquid droplets. And so for this, you'll use a different approach. I'll make the comment that I would say in terms of combustion modeling today, the state of the art, certainly there's a lot of maturity now in turbine combustion, the modeling of this problem, assuming that everything is happening in the gas phase. There's been a lot of headway wherein we account for the liquid phase as a collection of droplets. The link all the way down here to the atomization process has yet to be made. I'm not aware of any truly predictive simulation that starts from the fuel injector, from the nozzle, specifies a flow rate, and predicts pollutants at the other end of the combustor. This is something that, as far as I'm aware, has not yet been done. So this is a very, very topical area of research. Any questions, comments? I have, so what I want to do is, so I have a few examples, but I think you all know why you're working on multi-phase flows. I don't think you need me to motivate the area for you, so we'll go quickly through that. What I have in the next few pages is really just the basic equations. I want to introduce my notation. I'm going to use mostly vector notation for Navier-Stokes and all this. So I want to show you the notation. We'll make sure that we're on the same page regarding the boundary conditions, regarding how everything is written down. And then we'll derive the equations first for the particle-laden flow problem, for which things are going to be essentially trivial. And then, because we'll stick to a simple version of the problem, you'll see. And then we'll do the same thing for the liquid gas flow problem, where the equations are going to be a little bit more subtle, but not that much. Okay, and that's kind of where I think we'll essentially be at 11:30. So we'll be at the end of this first lecture. Yep.
So when we are dealing with particle vector flows, we are considering many particles. So and if the inertial effects are less, suppose, then don't we have to consider the interaction between those particles, like using some another physical model apart from the
So you're saying, don't we have to consider the interaction between the particles? Yeah. So in what situation? Say it again.
Like when the inertial effects are less compared to the viscous effects.
Yeah. So you're saying, if we have two particles next to one another that don't touch, shouldn't we account for their interaction mediated with the fluid, right? The fact that this particle will modify the fluid flow, and as a result, that particle will feel the effect of that particle. I absolutely agree, yes. So it doesn't change the fact that as far as tracking the interface, it is essentially the tracking of the centroid of a sphere that you have to deal with. In terms of how you do this tracking, this is where you'll have to say something about what are the forces, or what is the relevant velocity of the centroid of the sphere that you're tracking. So in terms of a numerical standpoint, my point remains that you only have to worry about where those two spheres are. You don't have to worry about deformation or anything like that, provided that those objects are solid or they're small enough. How you do this tracking will require you to either do a full DNS and say something explicit about what the flow field looks like, or it will require you to say something about the forces experienced by the objects, which will require you to introduce some models. Yes. So yeah, we'll talk about that. We'll explicitly head-on address a situation where the interaction between particles happens due to direct collisions, so actual physical touching of the particles. But I do agree that if you have sufficiently strong viscous effects, you will have to account for that regardless, even without contact. Other questions? Yeah.
When a drop falls on a solid surface, then can it be considered to be a three-phase flow where a liquid drop?
So liquid drop on the solid surface, I guess it depends on your modeling perspective, but this is exactly what I was essentially saying about, telling you about. So this is a triple phase flow. This is a situation where the very detailed physical process ultimately is controlled either entirely or at least modified a bit by the molecular scale physics of the contact line motion. So if your drop splashes with high velocity and you can say something about, say the wettability of your surface is such that you can assume a 90-degree contact angle and there's no hysteretic behavior, so the contact line just moves at 90 degrees nicely, no matter what is the velocity at which it moves. Under those assumptions, yeah, you probably can ignore the triple phase aspect of this. You can just say the wall is a boundary condition. But typically it won't be the case. Typically the drop will start wetting, the contact line will move, the velocity at which the contact line moves will impact the contact angle that you observe, and that will directly have an impact on the outcome of the collision.
Well, in my case, the solid is at a certain angle, and also the drop size is changing along the path. So will it affect something?
Yes, it will. Yes, so again, there's different regimes, but typically the fact is changing the wettability of the solid substrate can lead to a drop either bouncing completely or splashing completely, creating new ejected droplets or not. So changing the wettability will change the outcome of the collision. So yeah, even at an angle, yeah, it will have an impact. Other questions? All right, so I have a few examples of why those flows matter. I went with somewhat more extremes and maybe unusual ways of thinking about multiphase flows. I don't want to spend much time on this, so I'll just say quickly what each image is. I had lots of movies, but I don't have an internet access here, and they're all running off YouTube, so I'll have to at some point get connected, but I don't think we need that. But if you have a good particle tracking code, you can probably say something about a landslide, for example. That's a little bit of an extreme way to think about it, but the landslide is nothing more than a particle-laden flow well into the collisional limit where the interaction within the particles matter. So any type of debris flow, things like that. I don't know if this is the type of phenomenon you have here. I know it's pretty important in Arizona and Phoenix. They regularly have those type of sandstorms. They call that haboob. That's the type of thing that you can model. This is a particle-laden turbulent flow. This is the type of thing you can model with a particle-laden computational tool. This was so. There's you've seen probably a number of videos of the various spacecrafts that have landed on Mars recently. So this is, in fact, this was supposed to be a video, but what happens is when you land on a dusty or sandy planet without a significant atmosphere. The landing process will lead to those material that we call regoliths to be lifted up and potentially re-injected in the propulsion system. So this is a very interesting, this question of sand or regolith transport for space or non-Earth based landing is an important topic that NASA is researching actively, that JPL is researching actively. On Earth, a helicopter trying to land in the sand will lead to a similar phenomenon called brownout, where all the sand is being lifted up and is re-injected by the engines, and that can lead to pretty major failure. I'll give you one more example about what you can do with the type of tools we'll talk about. I know that, so there's at the National Technology, National Energy Technology Lab, NETL, in the United States, there is a big code, a big multi-phase code called MFIX being maintained and developed. It's mostly a code based on two fluid type approaches, so Eulean modeling approaches for particle-laden flows. One of the code users is someone who studies pyroclastic flows out of volcanoes. This is a very relevant way that you can make a multi-phase flow code come to good use. Energy efficiency, cold furnace, bubble slurry reactors, nuclear engineering. We've talked about all this. Any type of system where cooling is important and conversion is important, multi-phase flows will play a role. All right. What I want to do now is talk about the equations that we'll be solving. So really, my goal here is to give you a summary of the reference equations. We will focus here on low Mach number flows. By low Mach, I will still allow for variable density. Okay, so I will not assume constant density. We don't need that. But we will ignore compressibility. So starting from the single phase equations, we don't have too much to say here. I'll be calling the velocity u. The bold notation will indicate a vector. The pressure p, density rho, viscosity, the dynamic viscosity will be mu. And this will get the continuity equation, d rho dt plus divergence of rho u is equal to 0. So that's the vector notation I'll be using, okay? The Navier-Stokes equations, the same way, d rho u dt plus divergence of rho u dyadic u, okay? So this notation here, I don't know. It's funny, you go from one country to the next, people are used to different notations, but this is just a rho u, the dyadic product, leading to a second order tensor. Tau here is my stress tensor. It has the isotropic part with minus p times identity plus then mu times the symmetric part of the velocity gradient tensor. And because I've allowed for density to vary, I have to be careful and include the dilatation here. Okay? So that's my single phase starting point. Even though the equations we're using here are variable density, in the afternoon I will drop this. There's a couple of reasons for that. It leads to a very significant increase in the number of lines in the code to keep track of a variable density framework, because suddenly you need to be careful about momentum being different from velocity. You need to keep track of your density at different times. You need to make sure that the density and the velocity are matched up appropriately. it just blows up the size of the code in a significant way. The tools, as I will describe them this afternoon, are completely applicable and amenable to variable density. But again, my interest was to try to avoid having 5,000 lines of code to show you. It will be, I think, on the order of 1,000 lines of code, which a lot of them are comments, a lot of them are just spaces. So things will be reasonably readable, at least I hope. So there's going to be a little bit of a mismatch here between the details of what we write and the implementation that will be constant density. Let me see. So I don't have, one thing I should say here is that this I here is my identity tensor, in case this wasn't clear. And then we'll need no penetration at the surfaces and no slip at the surfaces. Okay, so that's going to be my boundary conditions. So now here's the very naive way with which I'm going to deal with particle-laden flows, with solid fluid flows. I'm simply going to ignore the fact that we're going to have many particles. And for now, we're going to say, let's think about one, and let's essentially write the closed form problem. So we're going to look at the full equations. We're going to say, well, everything is easy. If we can solve Navier-Stokes, we can solve this problem. So if this is the object, this should be like streamlines around, but somehow they don't really show up here. So this is my object. This is one of my many particles. I haven't assumed it to be spherical. I've separated my domain into an omega f, which is the fluid part of my domain, and an omega s, which is the solid part of my domain. My interface here between the two phases is called gamma. This is my phase interface. My object has a centroid, which is my x sub s. So at that center of mass, I have I can prescribe here a translational velocity and also a solid body rotation that I'm going to write here as an omega s. Okay, so this object is solid. It can only undergo solid motion, so it can rotate, it can translate. That's it. So now what I have to figure out is how can I predict the rotational velocity and the translational velocity. And for that, I have to integrate all the forces applied on my solid. Okay? Well, all the forces applied on my solid, essentially all the body forces and all the surface forces. The body forces, for the most part, will look at gravity, but you could have electromagnetism. You could have, well, not that many other forces, really. So let me say here, body forces will have the mass of the solid times the gravity. So that's the effect of gravity. And you'll have electromagnetic forces, meaning essentially the Coulomb force or the Lorentz force. I don't know. You probably call that the Lorentz force. QE, or same thing with magnetism. The surface forces, now they're just coming from the fluid stresses integrated along the surface. So this, we're going to write as an F fluid, which will essentially boil down to drag, what we're going to call drag. And that's going to be the integral over our bounding surface of tau dot n. Tau I introduced earlier as my fluid stress tensor, dx. So if I'm solving, if I go back up here, and I'm solving my single phase flow, if I prescribe the appropriate boundary conditions for my single phase flow at the surface, I can explicitly solve for it and obtain the full force on my object, add it to any other process like gravity, and obtain from equation 4 here the full description of the dynamics of the object. And then, of course, once I have the velocity, I can directly integrate the position because one is just a derivative of the other. And then we can do the same thing if we're not going to go through the details, but if you want to look at the rotation, you can do the exact same thing with angular momentum. This will be the moment of inertia of the object that you can compute from the shape of the object, and then you'll have to include the torque. Oh, I forgot one thing. Forgot to talk about collisions. So you'll have to include the torque generated by the fluid stress acting on the surface. So this is the same thing, but with an additional cross R term. It's a torque calculation. So let me, what did I want to say? Oh, yeah. So there's another kind of surface force that one should include, and that comes from direct contact. So you'll have to deal with contact mechanics provided that objects are in contact with one another. And so if multiple solids, I'll just say this. We'll have to include a contact force. And we'll do that. Oh, it's a contact problem. It's good? Okay. Okay, same thing. Contact between two objects will generate torque. It's just a cross R integrated over the surface. This is a simple calculation as well. Okay, so we'll need to deal with boundary conditions. The boundary conditions are essentially the same as what we've talked about before. We'll have no penetration of the fluid at surface of solid. So U minus US dot N at the surface will have to be 0, where N is the normal to the fluid, did I write? Okay, so where N, where N is this. Forgot to give you N. N is my interface, phase interface normal. So, no penetration and no slip. So at the surface, the fluid velocity should essentially match exactly the velocity of the object. So what we've written here misses the point entirely of two-phase flows. We're treating here our object floating around in a fluid as a single-phase flow problem. So we're treating a particle-laden flow as a single-phase flow problem. So this is all fine and good if you have one object, if you have two objects, if you have 10 objects, if you have 1,000 objects, if you have maybe 10,000 objects. Well, say 100,000 objects. Okay, 1 million objects. That's in fact the most recent publication that addresses particle-laden flows from that perspective. Comes from Marcus Hullman. It's published, I think, last year, or no, earlier this year. A paper where he, I think, is tracking individually using this type of approach, solving the flow around individual particles. Full DNS, everything is resolved. All scales of the flow are captured. at the surface of the objects is tracking on the order of, I think, 6 million particles. This is enormous, okay? Absolutely enormous. If you're looking at a gasifier, you probably have a few trillion particles. So this is ultimately not scalable to the type of problems we might be interested in looking at. However, it is extremely useful for discovery to help us understand how those flows work. We'll talk about methods that are scalable to the hundreds of millions, probably the billions of particles, which will allow us to get pretty close, certainly will allow us to look at lab scale type multi-phase flow reactors. We will not talk about this approach in more details. This approach, I'll just say this. This computational approach, or this computational strategy is referred to as particle resolved direct numerical simulation, okay? For those of you who've had exposure to the field of turbulence, direct numerical simulation is what you call a simulation where all the scales of a turbulent flow, so a single phase turbulent flow, are captured. What we're saying here is that we're capturing all the scales of the turbulence as well as all the scales involved with the flow at the surface, developing at the surface of the particle. For those of you with interest in this, I'll give a few names. You should look into the work of Marcus Ullman. You should look into the work of Shankar Subramaniam. There's many others, one of them being Andreas Prosperetti. The list is long. I'm not going to give you an exhaustive list, but those are some of the key names of people working in this area. Inherently, if you're doing that, you're not really embracing the multi-phase flow side of things. Let me zoom in a bit so that you can read. So we're not going to talk more about that specific topic. Or at least not if we don't, except if you prompt this via questions. We're going to look at the reformulation of those equations where we're going to provide a model for this. So we're not going to directly compute this. We're going to model this instead. So we're going to model drag. And as such, we're going to save an enormous amount of computational resources, and that's going to allow us to scale up the problem instead of being stuck to maybe 1 million particles with 100,000, provided you have 100,000 compute cores, you're going to be able to do 1 million particles, probably not on the laptop, but close to it, and you're going to be able to do hundreds of millions of particles on reasonably small clusters. Okay, so what we're going to do is did I unplug this again? No. So we will focus on approaches where FD is modeled. As a result, the cost will be less. Yes?
When talking the number of particles, will the volume fraction also be important? Simply based on particles?
Yes. So in the general sense, we don't know, right? You can imagine situations with many particles where volume fraction remains small, and situations where few particles where the volume fraction is large. But we'll talk, so in the notes that will cover not tomorrow, but I think the day after tomorrow, we will be explicitly handling the situation of volume fraction. What is the impact of volume fraction? How do you put that in the flow solver? This is another shortcut that I have taken. We will not be implementing an algorithm wherein we take directly this effect into account. It wouldn't be very difficult to do, but it would be on par with fully accounting for variable density. And as a result, it would kind of double the size of the code. It's nothing very problematic, but it will inflate the code quite a bit. We will talk, indeed. We will talk about what is the impact of accounting for this. I'll show you that, for example, if you want to get a bubbling fluidized bed, you better account for the effect of volume fraction, or else things won't work. So yeah, we'll talk about that. Okay, so we'll talk about how we go from these equations to equations that we can deal with more efficiently. Okay, let me finish up by talking about the equations that we'll use for liquid gas flows. For liquid gas flows, we'll use essentially the same set of equations. We'll essentially say that we have two low Mach number fluids, one liquid, one gas. It doesn't really matter. As long as they're unmissable, we'll just say that we have two fluids that obey Navier-Stokes. I've just introduced equations here where the fluid is written with a subscript alpha. We'll probably switch to 1, 2 subscript or an LG subscript to describe liquid and gas. But for now, you can have as many phases as you want. We'll consider continuity, Navier-Stokes again, and what we'll worry about is how you reconnect your Navier-Stokes equations at the interface between the two fluids. So, one thing I should say is, again, here we'll essentially say, or at least one of the things we'll say very soon is rho g, the gas density is going to be constant, and rho L is going to be constant. If you're in this situation, then what happens is that both the liquid and the gas are solenoidal, okay? So we'll be working with this for the most part. The Navier-Stokes equation are written here. The stress tensor, this is just essentially a copy of what I had before, so there's nothing particularly exciting here. What I want to say is essentially what happens when we try to reconnect the two phases. So this is our phase interface gamma separating the gas domain omega g from the liquid domain omega L. One is characterized by the density rho L and viscosity mu L. The other one, density rho g, viscosity mu g. I've added one thing, which is the surface tension coefficient. Are we blue again? No, not quite blue yet. Oh, we're blue. We're very blue. Okay, I know how to control it now. Oh, I guess not anymore. Oh, yes. Okay. So the interface between the two phases, what we're going to do is we're going to introduce a local coordinate system. We're going to introduce first a normal vector. I'm going to call n. Very sorry about that. And then I'm going to need two tangential vectors. I'm going to call one T1 the other one T2. So now I have a local coordinate system tied to my local liquid-gas interface. And I'm going to make use of that to connect my two sets of equations. So there's nothing too complicated. There's some derivation, but I've essentially typed it up, so I'll let you read that in more details if you're interested.
T2 is into the...
Yeah, so here T2 is... Oh, no, you're right. It should be going into the board. Thank you. Yes. So, our normal velocities will have to either match, or if they don't match, we will have to have phase change. So if we assume that we don't have phase change, so that we don't have a liquid becoming a gas or a gas condensing into a liquid, the normal velocity simply have to be the same, or else our interface cannot be a material interface. Essentially, you derive that easily by doing a control volume analysis on a small little pillbox volume that encompasses the interface. You shrink its thickness to epsilon, and you see that basically you cannot generate or destroy mass at the interface, and so the normal velocities have to match. That gives you essentially a reformulation at the surface of mass conservation in the form of u dot n having to be continuous at the interface. I'm going to write that in the form of these brackets. So this will designate a jump. Okay, so a bracket sub gamma will be a jump across the gamma interface. The notion of jump here, I'm going to, well, I think I wrote it, yeah, it's right below. So what I'm saying here is that it's simply the difference between the quantity on the liquid side and to the quantity on the gas side. That's it. So it's a simple shortcut notation that we're going to make use of. So this is derivable from conservation of mass. I have a little note here that you probably cannot read up here. You can hopefully read it on your printed notes. You can do the same thing if you have phase change. Then this equation changes, and it tells you what is the level of discontinuity between the velocities based on what is the evaporation rate. Okay, tangential velocities are going to be interesting. You are aware that when you derive the Navier-Stokes equations, the no penetration condition is something you derive again from conservation of mass. But the no slip condition is something you postulate. We cannot prove no slip in an exact way. We can simply state that this is the condition that seems to match the best all experimental observations. Well, we're going to essentially take the same process for the tangential velocities. And we're going to say that if we have viscous fluids on both sides, it is reasonable to assume that there should be no jump in tangential velocity across the interface. But this is something that we don't prove. This is something that we're going to assume. So we make that assumption that there's no jump in u dot t sub 1 and 2 across the interface. I don't know if I have a little note on that here. I should have. If you're looking at a model, a two-phase flow model based on the Euler equations, that's out the window. We don't have any condition anymore on continuity of the tangential velocity if you're solving non-viscous flow equations. All right? We just don't have anything. Slip is an acceptable solution from the Euler equations. So the interface could be a slip surface. Okay. From the momentum equation, the same pillbox analysis, a small pillbox control volume that shrinks. You go through that and you derive the continuity of normal stresses. So that means that the n transpose dot tau, the fluid stress sensor, has to be continuous across the interface, except if the interface is capable of withholding any type of normal force. Well, if we have surface tension acting, the interface ends up indeed being capable of holding, withholding a stress. So here, this is a very natural way for us to introduce a surface tension force. So if I'm in my little, that I'm seeing change of color here. Yes, okay. So in my little pillbox analysis again, if I have my interface like this, that interface we need to hire someone to hold this together. Will exert tension, so surface tension on both sides, leading to a normal force, a normal surface force, which is what shows up here in my momentum conservation. In the interest of time, since we're almost, well, we're actually going over a little bit, I'll wrap this up by saying that essentially at this point, there's a couple of things we need. We need a model for the surface tension. This we're going to write as a sigma surface tension coefficient times kappa. Kappa will be the local curvature of the interface times the normal to the interface that we've defined earlier. Okay, so this is going to be the way we're going to write the surface tension force. Once we have this expression, we can essentially turn it into three equations, right? Because this is a vector dotted with a second order tensor, so we effectively have here three equations. So we can write out those three equations and manipulate them a little bit. So that's what I'm doing here down there. I'm going to take that boundary condition and project it onto my n T1, T2 basis and express it in terms of those three contributions. The n transpose dot tau dot n will contain the isotropic term due to the pressure, because it will contain the diagonal. The n transpose dot tau dot T1 and T2 will not. I will not see the pressure show up, only the viscous stress sensor. Okay? So that gives you those three relations. And then you can manipulate them and simplify them a little bit. That's a fantastic engineering solution. Tape is oh, well. Thank you. So, we have those three equations. We can simplify them further by looking at what it means for a velocity to be continuous at the interface. So at this point, we have a normal velocity that's continuous at the interface and a tangential velocity that's continuous at the interface. That means that if I take the gradient of my velocity in the tangential direction, it should also be continuous at the interface. Therefore, there should be no jump. You have to be careful. The gradient in the normal direction doesn't have to be continuous at all. So it is possible for my velocity at the interface. So if that is my interface, it is possible for my velocity to look like that. It is completely acceptable for my velocity to have a change in slope. This observation, combined with the fact that the divergence of the velocity, we've taken it to be 0, that allows you to say that the normal velocity differentiated in the normal direction to the interface, that has to be continuous. So this is, we're not going through the detailed derivation here, but this is an easy derivation to go through. I'm basically giving you all the information here. But the tangential velocity to the interface can be discontinuous in its normal gradient, but the normal velocity to the interface has to be continuous in its normal gradient. Okay? So if you plug all this into equation 14, 15, 16 that we had written from equation 13 here, which was continuous, so the continuity of the conservation of momentum, you're left with this very simplified expression right here. And that's what we're going to make use of. What that tells you is that at a liquid-gas interface, the pressure is going to be discontinuous. The discontinuity will come from two sources, one that we'll essentially not care too much about and one that will be very important. The one that's very important is sigma times kappa. This is nothing new. If you've played with bubbles and all this, you know that there's a higher pressure inside a droplet or bubble due to the surface tension. So, by the way, so if I tell you that I have a droplet of or bubble of size of radius r and surface tension sigma, what is the pressure difference between the inside and the outside? Okay, now if I have a soap bubble, okay, 1% at a time, or one person louder than the others? It has a 2 because there's 2 surfaces. Yes. Okay. There is also an effect due to the jump in the viscosity. So if the viscosity on both sides is different, the pressure will also be discontinuous. We'll be interested, at least my interest, my personal interest, tends to be more in higher Reynolds number flows, where it is reasonable, or it is often the case that this contribution is less significant than that contribution. It's not always the case, and it can be that the viscous, the pressure discontinuity due to the viscous stress is important. Okay, so continuous pressure, continuous velocity, discontinuous pressure. Discontinuous. So one of the things we'll do next week is we'll derive the methodology for solving for the pressure in the presence of this discontinuity. How do you solve an equation for a discontinuous variable? It's something we're going to look at. So I had something on the inviscid limit. So I'm not going to mention that again. I think I've said it already, but the main point here is that in a general situation, if you're inviscid, mass conservation still requires continuity of normal velocities, but you don't have this assumption of a viscous fluid that allows you to require the continuity of the tangential velocities anymore. There is nothing you can say about it. You've just lost any constraint. As a result, also the continuity of normal stresses boils down then to the jump of pressure being equal to sigma times kappa. All right, I think those equations summarized down there, but I don't have anything to add on this. So at this point, I think we'll stop with this basic set of initial set of notes. So we've done some basic high-level introduction, and we've written down all our basic equations. From that, we'll start modifying things and zooming into a few specific questions, and but also talking about how we start building codes capable of dealing with those problems. I'm happy to take any questions if there are any. If not, I'll see you this afternoon and for the first tutorial fun time.
Term out there. Right. So how will it deal with it? It is discontinuous function. So do we have to separately define it for?
We've taken a very broad view at this point, right? So the question becomes what is the set of equations you ultimately discretize? If your perspective is based on those equations, then there's no problem because you're solving for everything here. We're talking about scale resolving simulations here. There's nothing except for the very details of the triple point physics, there's nothing we've swept under the table. Well, that's not quite true. We've swept under the table compressibility, and we've swept under the rug the phase change with this. But if you solve those equations, you can have a tiny bubble and a big bubble. You'll find that your pressure is the background fluid pressure that jumps up higher for the tiny bubble than it does for the big bubble, provided you have a technique that allows you to deal with a discontinuous pressure field. And so we'll talk about specifically one technique that will derive and that will fully implement in the context of our toy code that's called the ghost fluid method. So we'll do that, and you'll see that you can deal with this jump in pressure. And also what happens if, for example, your bubble is not quite spherical, but if it's squished, then yes, there is a jump in pressure, but the pressure inside isn't constant. So we'll solve for all this. Now, if your perspective is that your bubbles are a large collection of essentially spherical little objects that you're tracking in the Lagrangian way, then it's a very different question. But then also those are not the equations you would be solving. We would need to derive those equations from basically zooming out from this. Okay, so and we'll talk about some of those questions. Well, I was not necessarily planning on talking about bubbles too much. It's not necessarily my expertise, even though there's a lot of overlap between particle-laden flows and bubbly flows. Okay, other questions? Okay, if not, thank you for your attention, and I'll see you this afternoon.